All right, this is Chemistry Chapter 6, Lecture 3. This will be the third and final lecture of our Chapter 6 from the book. What you need for this lecture is you need your chemistry notes. We'll be starting at the bottom of page 5 and on your own 6.10. All right. You'll need a periodic table, a calculator, and you'll want to open your textbook to page 189. Okay, so the first one that we're going to work, 6.10, says, in one experiment, the empirical formula of a compound is determined to be NaPO4. In a separate experiment, its molar mass is determined to be 354 grams. What's its molecular formula? Now remember, the empirical formula is simplest form, so we're asking for the molecular formula, which wouldn't be in simplest form, okay? All right, so the first thing that you want to do, so 6.10, if our empirical formula is NaPO4, we need to add up the empirical mass. We need to get that. So for sodium, we have 1 sodium. If you look at your periodic table, each sodium weighs 23. So that's 23. We have 1 phosphorus. So that's 1 times 31. And we have 4 oxygen. So 4, each oxygen is 16. So that is 64. If you add that up, you'll get 118 grams per mole. That is the empirical formula. Now the molecular formula is going to be a whole number ratio of this empirical mass, okay? So it says its molar mass is 354 grams. So we need to get a ratio. Just take the molar mass, divide that by the empirical mass. So that's 354 divided by 118. And you get a whole number ratio of 3. So in these problems, you're going to get a whole number when you do this. It might be off by a very tiny amount due to rounding, like a 0.01 or something like that, but it's going to be really close to a whole number. To get the molecular formula, you take the empirical formula, which is NaPO4, right? NaPO4. Okay? And you multiply each subscript by 3 by this ratio. You're not putting a 3 out front, you're multiplying each subscript by 3. So if you do that, you'll get Na3, because Na was 1. 1 times 3 is 3. P3, 4 times 3 is 12, so O12. So that is the molecular formula. Na3, P3, O12. All right, if you want to pause while I erase this, we'll move on to next page, page 190. Let's look at 6.11. Okay, so we're going to use a process. I'm going to teach you a process to figure out from a lab experiment how you can get the empirical formula. So reading through 6.11, it says a compound is decomposed into 1.4 grams of sulfur, 1.39 grams of oxygen. What's its empirical formula? So we have to use our knowledge about a decomposition reaction. It's been decomposed, sulfur and oxygen. So you put the compound formula on the left. We don't know what the subscripts are. That's what we're trying to figure out to get this empirical formula. So SXOY, so that's what we're solving for. And it decomposes into its individual constituent elements. So S plus O2. Now remember, we had to put O2 because oxygen is a homonuclear diatomic. It's part of that 7 we learned, right? Oxygen's there. Sulfur's not in that 7, okay? So sulfur, not a homonuclear diatomic. Okay, so now we're going to use the numbers in the problem to figure out the moles of sulfur and oxygen. So for sulfur, we have 1.4 grams. We got to go to moles. So 1 mole of sulfur. Sulfur, you look it up on the periodic table, it is 32.1. Okay, so 1.4 divided by 32.1 is 0.0436. Let's take it out a few decimal places. That's moles. And these coefficients correspond to moles. We learned that with stoichiometry, right? So we're going to rewrite that equation in a minute and put 0.0436 in there. Now let's look at O2. Now you have to, it's not just oxygen, it's O2. You use the O2 that's in the formula. So we have 1.39 grams of O2. Put that over 1, change to moles. Get rid of grams. O2 is 32 grams. That's from the periodic table, 16 times 2. Do 1.39 divided by 32, and that is 0.0434. Moles of O2. Okay, so we're going to put that right there. So let's rewrite our equation. SXOY makes 0.0436S plus 0.0434 O2. Now we learned in chapter 4 when we were balancing that we can't have decimal numbers. It's got to be whole numbers. Okay? So here's the trick to change these decimal numbers into whole numbers. You want to divide each of these numbers, each of these decimal numbers, by the smaller number. Okay, so between 0.0436 and 0.0434, we'll divide this by 0.0434. It's just a smidge smaller. All right, so this is SXOY. Well, 0.0436 over 0.0434, if you put that in your calculator, it's just right at 1. So our coefficient is going to be 1. And then this one obviously is going to be 1, so it's just S plus O2. So now we can figure out how many sulfurs we have. Okay, X, you just count them up over here. There's just 1. How many oxygens? Y is equal to 2. You multiply the coefficient times the subscript. So 1 times 1, 1 times 2. So our empirical formula is just SO2. We plug the X and the Y in. We can't reduce that anymore, so we know it is an empirical formula. All right, I'm going to, beneath that particular problem, since it's a whole page, you should have enough room to work one more, okay? So I'm going to work from the book, example number 6.12. So turn back one page to 189, and we're going to look at the example in blue, 6.12, because I didn't think this example 6.11 was super great because a lot of times you end up getting a molecular formula and not an empirical formula that has to be reduced. So I wanted to work an example where that is the case. So let's do example 6.12 in blue on page 189. So if you read through that, so it's right here, it says a sample of brown colored gas is decomposed into 2.34 grams of nitrogen, 5.34 grams of oxygen. What's the empirical formula? Okay, so nitrogen and oxygen, so we put N sub X, O sub Y, that's we're trying to figure out the X and the Y. And we go through our decomposition rules. Well, nitrogen is a homonuclear diatomic. Oxygen is a homonuclear diatomic. So on the right side, we're going to have both N2 and O2. All right, let's check out N2 and see how many moles. So this comes directly from the problem. It says we have 2.34 grams of N2. So put that over 1. We've got to change that to moles so we can get our coefficient. So 1 mole of N2. Nitrogen weighs 14, so 2 times 14 is 28 grams. All right. So we'd have 2.34 divided by 28 is 0.0836 moles of N2. So we're going to put that right there. Then O2, the problem says we've got 5.34 grams. So let's change that to moles. Oxygen, from the periodic table, each oxygen is 16, so that'd be 32. So 5.34 divided by 32 is 0.1669. So that is going to be the number we can put in front of O2. So let's rewrite our equation. N sub X, O sub Y makes 0.0836 N2 plus 0.1669 O2. Now our technique to get rid of these decimals is divide by the lesser of the two numbers. So 0.0836, 0.0836. This is 1. That's going to be, if you put that in your calculator, it's going to be 2. It's right at 2. So we have NX OY makes N2 plus 2 O2. Now we can figure out X and Y just by counting up. How many do we have on the right? Well, we have 2 nitrogens on the right, so that's a 2. We have 2 times 2, 4 oxygens on the right. So our formula that we get from this decomposition process is N2O4. Now, is that an empirical formula? No, it is reducible. So then we must reduce this to NO2. All right, must reduce. So don't let that trick you. You go through all this math and forget to then reduce it to an empirical formula. All right, that does it for the on your own problems in the textbook. And I will talk to you next video.